Hello and welcome to today's Saratech Enablement Series. My name is Sarah Utsugi and I'm the Marketing Coordinator at Saratech, and I'll be your host today. Presenting today, we have Eduardo Sorto, who is a mechanical engineer at Saratech, and he'll be talking to you about NX CAD Drafting GD&T. All right. Hi, Eduardo. Thanks for taking the time to join us today. How are you doing?
Good, Sarah. How are you doing?
I'm doing well, thanks. So can you tell us a little bit about yourself and what you do at Saratech?
Yeah, so I've been with Saratech for 3 years now as a mechanical engineer, and most of my experience lies within the aircraft industry, aerospace industry, working on primary and secondary structures. I had some experience with tooling design as well with some medical device industries. And since my time in Saratech, I've dabbled in NX, Creo, SolidWorks. Now I'm learning CATIA.
Great. Well, we're excited to hear what you have to share with us today. Why don't you go ahead and share your agenda and take it away?
Yeah, thanks, Sarah. So good morning, everyone. Thank you for joining today's session. Today, we're going to be looking at drafting and GD&T using the NX tool. So the agenda for today is going to be giving a brief introduction to what GD&T is, what's the importance of using GD&T and using that GD&T language to define your tolerances and sizes. And then from there, I want to move into how to do this in NX. NX is a powerful tool. It has a lot of features in there. So we're not going to get to all the different aspects of drafting during this short time, but I'll give a good introduction to get you guys a good head start. And if there's any questions, anything specific you guys have, like Sarah mentioned, put them in the question box below or comment afterwards, and we can make some future content for you guys. So first things first is let's define what GD&T is. So GD&T defines the allowable deviation of feature geometry. So it stands for geometric dimensioning and tolerances. And so this gives you those allowables from your nominal designs. It communicates the functional requirements, and that's important. The functionality of your part. It does it for the form, profile, orientation, location, and runout of each feature of the design model. So most of you who are familiar with GD&T already have seen this famous table here where you can see the different types of tolerances, different descriptions and symbols for the ASME standards. So some examples include flatness tolerance, surface profile tolerance, perpendicularity, and so forth. Okay, another key part of GD&T is that it defines the inspection setup requirements. So when we're working with a drawing, you're really giving instructions to the person who's manufacturing this part and inspecting this part. So GD&T allows for a reference frame, these datums. So when inspection comes, you have some sort of reference, some basis to pull those dimensions from, as opposed to not having it. It has a lot more play in there. So this really communicates the entire design intent. So the best way to describe why GD&T is important is to go through an example of a drawing that has GD&T and one that does not. So this drawing here does not have any GD&T dimensions, right? All we have here is sizing from those diameter holes, the two holes here, the hole in the middle, and some thicknesses tolerances, right? Of course, this isn't fully defined, but this here is a good basis point if you're working with just simply GD&T. So let me go ahead and share my camera and go through an example of how this part will be inspected. And I've actually 3D printed this part so I can go through a live demo. Okay, so this is going to be a live demonstration on inspecting this part here. And so this is a part I 3D printed before this presentation, and it's the exact one that I have the drawing on. And so what I want to do with this part is basically inspect it using the drawing without GD&T and inspect it with the drawing that does have GD&T and compare the difference. So let's first start with the one without it. So what we know is we can, while we're inspecting this part to make sure it abides by our drawing, we know that the diameter for this hole is a specific amount, right? However, what it does not define is the orientation of this hole. So this hole, even though the diameter might be correct, the orientation relative to this surface here might be slightly at an angle, causing this to have either not fit with the interfacing component or introducing some unknown loads. So I check this diameter here, but I don't check the relative angles. So what can happen is this part can pass inspection, and however, down the line in assembly it can fail, or out in the field while the end customer or end user will be using this, it can fail there as well. Another thing is, if you notice here, this part is designed to be flat down here, but it's not. And so say this part can pass inspection by checking the thicknesses on both sides, a couple points, but using different inspection tools. However, if it passes inspection, it still might introduce some issues down the line. So let me show you what I mean. So for example, if we had a flatness tolerance on here, or sorry, if we did not have a flatness tolerance in here, what can happen is this can be a dome shape, like so. And so if you put this on the surface, you'll notice that if I try to mount this to the interfacing part, and I introduce some clamping force here, so this gets mounted here, here, and now what I'm doing is introducing some stress at this radius here. So again, it can pass inspection, everything can fit together, but now you introduce preload that could have been avoided if you had a flatness tolerance on this surface. Same thing applies if you have a true positional tolerance on this one versus just using the dimensions relative to a couple other features. You can definitely miss the mark if you don't have any datums defined from there. So jump back to the PowerPoint here and go over some of the pros and cons of GD&T. Okay, so let's summarize what we just went over. So what are the implications of not using GD&T? So the very first thing is the quality inspection might not capture the entire functional requirements of the part, right? We noticed that even though the diameter might be correct or the whole diameter might be correct, that there's no way to verify the orientation of that hole. Likewise, the thicknesses might be correct in certain places they are measured, but if the flatness of this section here that has some sort of lob here, it's now introducing different loads that probably weren't accounted for. So again, this is introducing risk into your part that you can probably get away with for some time, but eventually, if it goes unchecked, it'll come to bite you. So so there can be some failure during the assembly process when you're putting everything together. There might be some interference in there, or even worse, there can be a failure out in the field. So when the customer has this product at the end and they're using it, if there's a slight deviation from the design intent, then that can cause some failures as well. And that in turn turns into cost and schedule. So now what needs to happen to repair this is you need to have a root cause corrective action process in place to find where the issue lies, how to correct this issue, and then rev drawings. And it's in engineering, it's very expensive to rev a drawing for even the slightest thing. So you want to be very careful of to not properly tolerance and dimension your parts. So let's take this example a little bit further and now take a look at the GD&T features on it and what's being defined. So let's take the section view first. And first thing I look at is where are the datums placed. So we see there's a datum A here, datum B is the center hole here, and then datum C. So we have datum A, we have a flatness tolerance of 0.6 on datum A here. We have a surface profile tolerance of 0.2 relative to A here, 0.4 on the top surface there, and another one here. So what you'll notice is that the tolerances that are defined on these surfaces here are probably mating surfaces, right? If there's going to be a part that comes here or connects here, you want to make sure that any surfaces that interface with another component is properly toleranced. Okay, so those are form and profile tolerances. Now this is a positional tolerance, this true position tolerance of this hole. So without GD&T, you really have just the your dimensional tolerances to place this hole. But with GD&T, now you define that even further. Have a true position of a 0.14 diameter hole. So this is your area at maximum material condition relative to A and B. This one's here's has no play, 0 at maximum material condition relative to datum. Okay, so that's what we're working with. Now, the next part here is how do we translate this into NX? And a good example or a good exercise is to recreate this drawing in NX and show you where all the features are. If you've used GD&T before with NX, you'll be familiar with most of these settings. But if you've not, then you'll get a very good understanding of what your NX capabilities are. And what we plan to do here is introduce the subject, and then we can go into more advanced exercises and settings down the road if it's if that's what most people.
Oh, there you're back. You're back. So Eduardo, you cut out for about a minute. Will you go ahead and just cover that again?
I'm so sorry about that. But what I was going over this slide was basically the different what the different GD&T features and feature control frames here are defining on this part. So I apologize if I'm repeating myself, but this here is defining the flatness tolerance of this this surface here. So this is a form tolerance. This here is the surface profile tolerance, defining this top surface, this one here, and this one here relative to datum A. So this is a feature-to-feature relationship that's happening to your primary datum A. And so one of the key parts here when you're adding GD&T tolerances is your tolerances relative to your subcomponents and whatever you're interfacing. So as you can tell, this is a interfacing surface, this one as well, and this top part as well. Okay, now on the left, we have our positional tolerances. We have a true positional tolerance of 0.14 diameter at maximum material condition relative to A and B and A, and this one as well. So what you'll notice is that we have our primary datum feature defined here. A, B is the center hole, and C is the top hole. Okay. Okay. So now what's the result of having GD&T? So there's three key things here. It accurately communicates your part intent and function through the design, manufacturing, and inspection. And we saw that inspection portion during the live demo, right? We talked about how the boss here, without GD&T, we check the size and the diameter checks out, everything's great. But it does not have the feature-to-feature relationship that we might want relative to, say, surface A, right? So this can have an angle and still pass inspection. However, it does not capture the design intent. Okay? And it has more precise depictions of part features. All right, so now that we went through an exercise of an example of with, without GD&T, some of the key, takeaways of why someone would use it. Now let's go through an example and show this in NX. So the best way to go through this exercise is to take a drawing and recreate it in NX. And so we'll start off with this simple design. If this is a popular topic, we can go into more advanced features of GD&Ts, like those datum targets, surface datum target points, compound reference frames, and so forth. But for now, let's get started with this. We'll go through an overview of what are some different options in NX, different settings available, and we'll go from there. Okay, so let me open up NX, and the first thing I want to do is just start off with the views. Let's have this clean design. I'll pull up this on the side here, so we can follow along and recreate this drawing here. So the first thing I want to do is let's work on section A and define the datums. So I know that my datum A is going to be this surface. And there are a couple of reasons why you would go with this surface. Some industry standards is pick the largest surface. So when you go ahead and manufacture or inspect this, you have a flat surface to reference. So this would lean against some sort of table here. Okay, so let's define our datum A here. So this top annotations group here defines your datum feature symbols, your feature control frames, and your datum targets. So these are the three icons that we'll be working with today. So let's define our datum A. So we have datum A just as a floating icon. Let's go ahead and select a leader in here. And so you have a couple options, a couple different types of leaders. You can go with a datum, or you can go with a flag. So both of these are the most common ones I've seen for a flat surface like this. So because the drawing had a datum leader, let's go with that. And so what we would do is basically click on that surface and then drag this out. If you hold shift, you can move this up and down, right? And then just place it wherever you see fit. I think the drawing had it here, but it's easier to read if it's slightly outside the view. Okay. And now we had a flatness tolerance of 0.06 on this side here. And if you notice that the call out for that was in a flag format. So let's go ahead and do the same thing. We'll add a feature control frame of a flatness tolerance and have a flag feature on there. Okay, so we'll click on our feature control frame, and you'll see there's a lot of different options you can go here. The characteristic is the table I showed on the PowerPoint slide. So you have all your different forms and profile tolerances here. So let's click on flatness. And so there are a couple things you can do. I like to set it on the view first and then manipulate it just so I can have the static. So let's do that. Let's place it first. I can middle mouse click to get out of the view very quickly. And let's change the parameters of this tolerance. So we know that's a 0.06, and we know that it has no datum as a reference. So the important thing to know is that it does not have a datum as a reference because this is a form tolerance. It's not a positional tolerance, so it's not referencing a different feature or datum feature. So let's go ahead and click on that. And then from there, let's select our flag as our leader type, and then click on our surface there. So same thing, you can drag this out however you like and have this separate. I've also seen ASME standard drawings where we have the flatness tolerance tied to the datum A here. So you can also have this on below here and associate it to the view. Okay. So next thing we have here is let's do the same thing for the surface profile, but now let's do it with this this leader instead. Then from there, let's go on to something a little bit more complicated, these true positional tolerances. Okay. So again, we'll go back to our feature control frames. And if you're selecting multiple frames, what you can also do is inherit some of these, some of the previous feature control frames. So you can grab this and then use it as well. So that's just a quick tip to be a little bit more efficient. So that would help when you're working with those profile tolerances. So let me change this. Profile tolerance of 0.4. Okay. And this was relative to datum A. So I'll go to my primary datum reference. I'll pick on A here. And I noticed that this top surface here was using a plane leader. So I'll go ahead and do that and place it. And so the other one was right here. So let's do that really quickly. We'll set one here. We'll use our trick to inherit this feature. And now we can go ahead and use the flag type to grab this surface and bring this out. And I believe this had a 2x on the left. So a neat thing you can do is, some people add an extra annotation, text box here, but you can actually include that 2x as part of your feature control frame text here. So I'll add that as my 2x. You can add a couple of different comments down here as well if needed. So that's also nice to know. Okay, so very quickly I was able to add that using the inherit tool. Okay, so that defines those two. There's no cutout in the model, so I won't go through that. But let me jump into these true positional tolerance just because we have 5 minutes left. Sorry, I had connection issues halfway. But let's place some center lines in here using the center mark tool. I want to first create a dimensional tolerance. So let me add my radius in here and call this out. And from here, I can go ahead and add now a positional tolerance. Okay. So let me place this first. And I'll want to tie this to this part so it's all one, right? I can move this here so it has some room for that feature control frame now. And let's modify this so it's a true positional tolerance of 0.014 diameter at maximum material condition relative to datum A and datum, sorry, that was the wrong one. Relative to just datum A. and this was 0 at maximum material condition. Okay. And let's move this out a little bit further. So there's some room here, and there was a datum B attached to that feature control frame right here. Okay, so we can click on this, change our letter or datum identifier from A to B, click on our leader object, attach it to this, and just drag this out. And so now this acts as one unit, right? Okay. So the same steps are applied to this top hole here. Let me do that very quickly so I have enough time to answer some questions. So I'll go through that again, add this on here. But now I'm adding a feature control frame, attaching it to this box, attaching it, there it is, to this box. I'm going to inherit that the feature control frame from this diameter there, and go 0.014 relative to A and now B. Okay. Move this out, and I'll have datum C in there. Okay, and so that was a quick demonstration of how to place those two. Again, very simple, but there's a lot in there that we can explore. So let me go back to the PowerPoint and open it up for questions.
Great. Well, thank you so much, Eduardo. I really enjoyed your presentation. It does look like we have a few questions, but at this point, if anyone has any questions, please go ahead and enter them into the questions panel, and we can get to them now. So the first question comes from Daniel, and he says, when referencing a datum or datums in a feature control frame, should the primary datum always be included?
Yeah, so that's a good question. So I think the best way to answer this is to go to this first slide here. And so the question was, in the feature control frame, does the primary datum need to be in there? And so what you'll notice is that when you're using a form tolerance type, this is for individual features. So this does not reference a datum or a primary datum or secondary datum feature. This is on its own. So when we went through the example for this guy here, you'll notice that it's not referencing primary datum. However, the surface profile it's referencing datum A. So what this is doing, it's basically saying, okay, let's say within 0.4 of a tolerance relative to this surface, and so this can move, this much. However, this surface does not require that. And so if you check this graph here, you see the profile tolerance. It can be for individual or related features. So for related features, it's referencing that primary datum feature. And for related features, this section here, this all needs to have a datum to reference, whether that be the primary or secondary, depending on where it is.
Great. Let's see, we have another question. It says, does a different order of datums in a feature control frame change the way a part is inspected?
Yeah, it's a good question. So I can go through, show this for example. So say, for example, this hole, this true position tolerance hole, if we're reading this feature control frame, this is saying that there's a true position tolerance of 0.14 diameter relative to A and B. The first datum here is what this hole is normal to. So if for some reason this surface is datum feature B, then this would have B first and then A. So what the inspection person will do is basically reference B as the primary datum to relative to where this hole is placed. So it has that bonus perpendicularity tolerance to datum A, or B, whatever this would be.
Looks like we have one last question. It says, how do I create a compound feature control frame and features?
Yeah, that's a good question. So that's let me show you that in NX. So that goes one step further into the capabilities of NX, right? So if we go within this feature control frame tool, you'll see that there's lots of different options you can add here. You can add tolerance modifiers, but the actual compound datum references are going to be down here. So if, for example, you had a compound feature for datum A here, you can add that on there. Then you can add a new one in here. So you would add a new set and say maybe this is relative to B, right? So when you add that in here, now you have from A to B. So that's where you have your compound datum reference. So I hope that answered the question.
Yeah. Thank you so much for attending. Eduardo, thank you so much for your time and for your presentation.
Yeah, thank you, everyone.
Yeah. Have a great day, everyone. Thank you.
Thanks for checking out our channel. If you like what you saw, make sure to like and subscribe down below so you don't miss out on any new videos. Follow us on LinkedIn, Facebook, and Twitter for the latest engineering news and information. And to see all of our upcoming events, please visit our website at saratech.com/events.